First, Judy and I would like to thank you for coming, and I particularly would like to thank you for coming, because being a patent attorney is kind of a strange kind of a person, and it's not too often that you have a chance to kind of show off a little bit, and so this is an opportunity that I thought I couldn't pass. And I think it's anybody that's been in the legal business knows that it can be kind of dry, but being a patent attorney is a lot of fun, and you meet a lot of interesting people. And today we get to talk to David Criswell, Dr. David R. Criswell. David has been a very long time friend and client. A moment is that, for example, the first patents we were able to achieve for David have already lapsed. And so it's over 25 years or so that we've known each other. It was interesting also, and David will elaborate on this a little bit further, but I was initially introduced to Dr. Criswell by my brother-in-law, David Gross. And we have a lot of Davids around here, so we may get confused. But David and David were working together, and David Criswell needed some information in the patent business, and so my brother-in-law kindly referred him to me. And it's been much fun for me in my life ever since. He thinks large, and so he will explain to you those things. Our office in the history with David have gotten for him about 8 patents, and we have 8 different international patents for him for his various sundry U.S. patents. David is pretty well known in the area. He has spoken before Congress on space science matters. They didn't listen to him, but he at least spoke to them. He's quoted in papers, and he's done televisions and History Channel bits about space science interest things. He is currently, and he's just retiring from the Institute for Space Systems Operations, ISSO, out of the University of Houston. He's been running that organization for quite a while. He brought in a lot of money to the University of Houston for doctoral programs and postdoctoral programs. And he is just in the process of retiring, and so he's right now on a 2-month trip around the West Coast. David got his Bachelor's of Science in Physics in 1963 and his Master's in Physics in 1964 out of the University of Northern Texas. He has a PhD, he holds a PhD from 1968. I mean, you shouldn't be too impressed with a PhD from 1968 because then the science was easy. If you had to get a PhD today, you'd have to know a lot more. He does, yeah. And anyway, his PhD was in space physics and astronomy. He has written extensively on space science matters. If you ever have a chance to see his list of writings and seminars and the stuff that he's done and the work, avoid it. It's kind of boring, and it's too long, and it takes too long, and it's kind of an interesting thing in words you don't know. So in any event, let me introduce to you my good friend and client, Dr. David Criswell.
Well, I cannot express too much appreciation to the Howlers for the past 25 years, and particularly for this evening. It's just a marvelous turnout, and I'm really looking forward to not only talking to you, but with you. And before I get to that, I want to again thank Dave Gross for bringing the two of us together. Dave and I worked together for about 3 years on a congressionally mandated study back in 1984 of how to plan automation for the space station and the space station program. And it actually had a good effect on this unusual event. But you've got this 2 pages. On the back are these 2 posters. And what I know some of you are too far back to read all the details, but I'll start with the one on the far side, and then we'll move to what's covered by the patents that we want to talk about tonight. This focuses on electricity. Electricity is very, very important to every developed nation and every nation that wants to develop into a developing nation. That's why China is building one gigawatt coal-fired power plant every week. and has been doing that for years now. But we live, essentially, our electricity basically comes from fossil fuels. Most of it comes from coal, and we spent about a third of the fossil fuels we use worldwide are devoted to making electricity. And that ratio is going up with time. By 2050 or 2080, we'll probably be a 100% electric world. So everything will go into electricity. But we do it by mining coal and then transferring it by rail, as Warren Buffett knows, to tens of thousands of coal-fired power plants all around the world. We also gather natural gas and take it directly to the power plants, or we take it via ships, liquefied natural gas all around the world to make electricity. And then oil is primarily used for transportation, but in places like Saudi Arabia, oil is used to make electricity and also desalinate water. It just depends on what your local resources are. But the end result of all of this is that this is 2006 copyright. By that time, we were burning about 3 billion tons of carbon and hydrocarbon a year to make our electricity, and that resulted in 10 billion tons a year of CO2. Now, this number is about 15% higher since 2006, just due to the electrification of China and India, and it's growing exponentially. And what comes out of these tens of thousands of power plants all around the world is this flow of CO2 and also ash and other waste, and you can't collect them efficiently. They just go out into the environment and they accumulate and do their damage, such as global warming. But also, every breath that you take, you're breathing some sulfur from China or ash from China. Now, is there another, and these systems of transportation of the carbon and hydrocarbon fuels are massive. I don't know how many times I have looked at trains, 100-unit trains going across the U.S. to deliver from Montana to the East Coast the coal to run these plants. Now, is there another way to do it? Well, what John and I have worked on and worked out and obtained U.S. and Russian patents on, and patents on many others, is rather than having tens of thousands of power plants spread out all over the earth and then collect and close generally to cities and industries, instead centralize them into a few massive installations, it probably is hundreds to thousands, and site them very near the coal, oil, and natural gas fields that provide the carbon fuels. That way then, when you burn this carbon and hydrocarbon, you can re-inject it. First, you can use more efficient generation options, 10–15% more efficient to squeeze more energy out of it. But also you don't transmit or transport all of that heavy fuel all across Earth. Instead, you burn it right there and then re-inject most of it back into the earth, into the mines and the oil wells and the natural gas fields from where you got it, and you can use this material to release more fuel. And so you can extend the life of these various fields. You get methane out of coal fields, you get more oil out of oil fields. The U.S. is the most explored oil-producing nation on Earth. And a reasonable estimate is we've only extracted about half of the oil that's available. By doing that, you do two things. Instead of distributing your waste all around the planet, you concentrate most of it back into the source region, and you extend the lifetime of these fossil fuel resources. The next thing that you do, though, is change the electricity into microwaves. This is like radar. It's simply large area radar, which has been in operation since the 1960s. Most of the technology was developed to detect Soviet bombers and ballistic missiles back in the 60s. Some of these have been in constant 24-hour operation since 1960s. And this is low intensity microwave, about 20% of the intensity of sunlight. and it's transferred up efficiently, very focused beams, up to relay satellites in orbit around the Earth, which send the power back as microwave, and then it's converted on the order of 90% efficiency back into electricity. So think of the difference of Chicago with power plants all around it, or Manhattan with power plants all around it, producing this waste, versus actually smaller areas of receivers that just output electricity that has absolutely no physical contamination associated with it. And so what you can, and also these transmitters do not care who produces or what system produces the electricity. It could come from wind, it could come from hydro, it could come from local solar. Well, one of the things that happens in Texas, which has the largest collection of wind generators in a given political area, is that wind is not produced when it's needed the most in Houston when it's 105. It tends to be different parts of the day. But if this could go over to a transmitter and then be, when it's being produced and then being provided to China or India or England, then it would increase the efficiency of use of these renewables, which tend to be very, very, very variable. Same as if you had solar in Saudi Arabia, which has oil, and Qatar, which has enormous supplies of natural gas. You could convert it right there and send it anywhere in the world when it's needed. And so for companies in the US, where we hope we can see this started, whatever energy, whatever power source you have, you can, with this system, provide it worldwide at its highest selling price and still provide power to your area. And that's the basic guts of it. What we're trying to do, or what we are doing today on the planet Earth, is moving billions of tons, tens of billions of tons of matter all around the planet. And accidents happen. The huge tanker that foundered in the English coast about 5 years ago and muddied up or oiled up a lot of the French coastline, that sort of thing would not have to happen if you never move the molecules far from where they're changed into electricity. And so this would give away a means to take energy production, power production anywhere on Earth and provide it to virtually anywhere else on Earth. I promised John to keep the presentation short, and that's really the guts of it. There's technologies here that people in the area would question, of course, but there's a large background on this. The beaming of power, as I said, has been demonstrated since the 60s and 70s, partly under a program supported by the Department of Energy and NASA in the 70s to look at building satellites in space that would supply power to Earth. So they studied very extensively the beaming from large power sources, the handling of that power in space, and its reception back on Earth. Radar technology has been an operation that came out of the Cold War that supported most of those developments. The space shuttle has flown radars that have generated beams back to map the entire surface of the Earth over 3 different flights. And again, they use phased array radars that operate at about the power density that is required for commercial transfer of power. We have a huge technology base to draw on. It's not exotic technology. You're not trying to make something that may be feasible in 40 years. This is basically drawing on stuff that we've done since the Cold War. I think that the cost of this transmission and reception system can come down to the order of about 1 cent a kilowatt electric hour. So it would be a much less expensive way to just transmit power, but it would also eliminate the very expensive and environmentally disruptive operations that are required now on the planet. I think at that point, John.
Maybe talk a little about Mr. Brown and his initial tests of these things.
Well, Bill Brown was with Raytheon for over 20 years. Raytheon was the company that basically brought radar into operational existence during World War II.
Brown joined after that, but there was a 3-year period, a 4-year period from when radar was demonstrated in England in late 1930s, to where it was present on every ship of the Allied forces by 1942. And so when people really want to, are pressed to do things, it's amazing how fast we can do things. Bill Brown was the first person, as far as I know, to get in deeply into the technology of how you form power beams at commercial scales, basically using magnetrons. And a magnetron is not an exotic device. Every person in this room has a magnetron in their house. It's inside their microwave oven. And the microwave ovens, cheap ones, can sell as low as $15. So the magnetrons, mostly made in South Korea, sell for about $1. And that means this transition from electricity to microwave costs you a tiny fraction of a cent per kilowatt of electric hour, and they'll run for years. So that's the kind of exotic technology we're looking at here. But anyway, he first demonstrated the power beaming on a lab scale back in the late 60s, and then during the solar power satellite studies back in the 70s, JPL at the Goldstone planetary receiving facilities in Goldstone in Owens Valley demonstrated the transmission of power over a mile from one of their large antennas to a receiver that was essentially made out of styrofoam and small FM diode antennas. It was a bunch of graduate students put it together. It operated at 85% conversion efficiency from microwaves back into electric power. So you would aim this big 90-foot diameter antenna at this styrofoam set of receivers about a mile away, light up a bunch of floodlights, you move the beam off of it, and the floodlights would go out. When you scale this up, again, you can refer to planetary science radar to know that it will work over enormous distances. I think everybody here has probably seen pictures of the 1,000-foot diameter planetary radar in Arecibo, Puerto Rico. It shows up in James Bond films quite often, or in who's the woman that Contact? Yeah, Jodie Foster. And that radar operates at about 20% of the power density that you would like for sending radar around the Earth as power beams. And it has taken pictures of the moon for something like 30 years. This is done so precisely that they can take pictures of the south pole area of the moon a year apart and then subtract them from each other and do contour maps of the south pole of the moon to about a meter resolution. The large receiving array in Socorro, New Mexico, called the Very Large Array, is purely a receiver, but there's a thing in electrical engineering called reciprocity. If you can receive, you can transmit over the same path. And that radar has taken pictures of the moon the same way, and it operates over a receiving area of about 30 kilometers in diameter, which is more than enough to send if it were used as a power transmitter, to send power beams about a quarter of the way to the sun.
David?
Yes.
Do you have time for a few questions?
I was.
Just one more thought about the distinction between this and space solar power.
Well, as I said earlier, or I thought I said, this technology and our concepts of this came out of a $30 million study from 1974 to 1980, a joint study conducted by the Department of Energy and NASA on the concept of building satellites on Earth, or building the parts of satellites on Earth that you would then put into orbit and assemble into a structure that's about 6 miles by 12 miles on a side, send it up to geosynchronous orbit. It would accept sunlight, change it into microwaves, and beam that from geosynchronous orbit down to receivers on Earth. That was stimulated as a response to the energy crises, gas crises in the early 1970s. At that time, it was decided that that approach was not economically feasible, and that's been reaffirmed because of the expense of launching stuff from Earth. But in this case, you're not building huge structures in space. The power originates from conventional sources on Earth, and it's sent to receiver retransmitters in orbit around the Earth that are on the order of 1% of the size and mass of those 1970 power concepts. And it turns out, as you get into the numbers, that these can provide a very inexpensive way to retransmit power. To put that in another perspective, the Department of Energy has studies that indicate that if you just wanted to rewire the long-distance transmission of electricity across the United States, you'd be looking at an investment on the order of $5 trillion. A lot of that is the cost of going through just the physical construction, like the physical construction here, and also the environmental disruption. Here, you can eliminate almost all of that by putting your complexity or your retransmission in space, and then these beams weigh absolutely nothing. And so you can have considerable economies of scale with this approach, and much more flexibility.
So what are the obstacles, political and otherwise, to doing this?
Well, the political are, as they always are, they're the entrenched interests that want to keep doing business as they are, even though their business is becoming more and more difficult and more localized. Here, this would open up power producers in the U.S. to provide power anywhere and also start radically decreasing their environmental impact.
So be more specific, whose ox would be gored as companies?
The railroads for one.
Well, the railroads for one. I mean, that's most of the mass that we move around in this country is coal and oil through pipelines. So most of the oil that's moved in this country is for transportation, but most of the natural gas that's moved is for electricity. About 10% is for chemical industry. On the other hand, gas, if you go back 5 years, natural gas was very expensive. Now with the discovery of shale gas, we've got more shale gas than we know what to do with here. With a system like this, shale gas could be used to power a much larger market than is conceivable here. So it's a transition. And part of what brought John and I to this point is how can you roast the ox rather than gore it? That's not the right analogy, but I'm struggling. How can you give the ox a broader range? And this seems to me it's the way it could go. The thing to remember is that, yes. Okay, let me finish this one thought. Only about 15% of the world has affordable electricity. And so as long as we confine our energy producers to small areas, that's not going to grow. This is a way to provide that electricity to almost anywhere in the world at more or less the same price. Okay.
Are you aware of any other governments or even the UN that might be considering this technology?
There is an interest in China about the solar power satellites. I can't see that would be a competitor here just due to the expense of putting them up. But this is a new idea. That's what the patents have certified. Mm-hmm. Yeah, either.
Yeah, you mentioned the microwave oven and then roasting oxen was mentioned. I noticed when I put my cat in the microwave oven, he doesn't like it. So my concern is, with this high energy density going through space,
Mm-hmm.
about the safety of those beams, and if the airplane flies through it, what happens, or if it's misaimed, what happens?
Okay. It's a matter of intensity. This was a very serious consideration back in the 70s, and still is. How intense can the beams be? And the nominal baseline was about 230 watts per square meter going through the atmosphere for these beams and at the surface of the receiver. At the surface of a receiver here. Now, At that intensity, you could walk into the beam, you would feel heat warming, just like Bill Brown's demos of transmitters inside of a room this size. You could walk into the beam, which was actually, in his case, operating at 4 times higher intensity. You'd feel warmth, but that's about all. And the reason is that each of us are a little heat engine. And if you're like you're standing, or I'm standing right now, we put out on the order of 100 to 150 watts per square meter. Now, as a beam of 250 watts comes through us, we find that we're a very lousy microwave antenna. We only absorb about 2 to 3% of that. So even at the max, we get about 10, 18 watts per square meter. Just a fraction of what we're putting out is a little heat engine. As far as stray radiation is concerned, and there will always be leakage out of these systems, we're also microwave transmitters. In this frequency range, we would be putting out ourselves, just because we're at 300 degrees Kelvin, about as much stray radiation as you would have from a system like this. So you have control over that. You have a rheostat on it. You can put peripheral fences around the receivers and the transmitters so that virtually all life is excluded from it. They're industrially zoned areas. And planes flying through them would go through so fast, and generally metal skins would absorb all of that you wouldn't be exposed to it. So it's a choice, but it's a choice that we've got the freedom to make, and to make in an understandable manner. Whereas, how much freedom do we have over this? Over these waste products which just accumulate rather than are transient? Yes, sir?
If this technology is readily available, why hasn't there been any use of it in terms of testing? And what would it cost, let's say, if you were to set up a test site in San Diego, to take it from Montana up to the satellite to beam into San Diego to run a city like La Jolla?
Well, I'm still stymied by why it hasn't been done. I mean, the operating elements, as I said, go back 30 years or more. I think, it took the steam engine 150 years to go from concept to first use, and the first steam engine to pump water out of English mines operated for 200 years at low efficiency. So we just adapt slow, but this is a much more rapid adapting environment. I think we're going to be driven towards something like this. Now, as far as the cost, I have done models of the cost and the engineering based on the studies of solar power satellites, the work of Bill Brown and many others. And I think at an industrial scale, as I say here on the back, or on the type part of this, point number 5, I think you could get to a demonstration of the beaming for about $2 billion, and these are rough numbers. A demonstration of the reflectors, redirectors, for about $5 billion, and the receivers for about $4 billion. And those could more or less be in parallel. You would, I don't see the transmission as being particularly challenging. It's more, or even the receivers. The retransmitters are the most challenging part of it. But as I said, these, and note in more extent in the patents themselves, which are available up here, and in other stuff that I've published, the handling of microwaves in orbit is something that has been worked on and demonstrated extensively by NASA, and particularly by the Department of Defense. So we're not going into this blind in any manner.
How many of these satellites can you put up in the geostationary orbit? I mean, it's pretty crowded up there now, from what I read. It used to be like 5 degrees separation,
Mm-hmm.
and then they reduced it down to 3. It took more time for satellite up there.
Okay, the question is, how crowded is geosynchronous orbit with satellites? They are on average about a degree and a half or 2 degrees apart now. And all of those are pretty small structures, except for a few highly classified but visible DoD radar surveillance satellites. This is not confined to geosynchronous orbit. I would think most of these satellites would be in medium altitude orbits with a low perigee, and they would be located at higher latitudes, because most of the energy users in the world are around 45 degrees plus and minus, especially plus latitude. And I don't think there would be a particular interference with GEO. On the other hand, when this technology gets underway, it would change the character of your geosynchronous satellites. You'd probably move them into, they'd be much higher power and far fewer of them. Gentlemen, but yeah.
In order for the, theoretically, in order for the capital investment to make some kind of a reasonable return, what would the cost comparison be to the consumer using this technology versus our current situation?
Well, our current situation is that costs are rising, except in the case of the natural gas. Nuclear is rising, coal is rising. We still are not facing the full impact of the environmental damage of releasing all of these waste all around the world. So if you look at the latest cost in the U.S. of just building a nuclear plant, those are going up to the point that they would expand, or more than the rough demo estimates here. The advantage with the electronics is, over time, for highly repetitive structures, the costs tend to drop. So I think you'd get into a better economic competitive environment with time. Let's see, I'm sorry. Someone over here? Yes.
What about national security issues?
Well, we've got a CNN news release here. The Pentagon, or the DoD, is the largest single user of energy in the U.S. economy. And there are wartime remote deployment situations where they pay the equivalent of $40 a barrel of oil and have great difficulty in maintaining the security of the supply lines to get it there. So this would be a way, at least for the electric uses, to essentially bypass all of that and make electricity available virtually worldwide.
Worried about vulnerability if we began to rely on these transmission methods. It seems to me they would be pretty vulnerable.
Well, I don't know why they would be particularly vulnerable. You'd have to, the main vulnerability would, these are dispersed structures. You could take out quite a bit of them and they'd still operate at some reduced level of efficiency. These are high above Earth, and people would have to go after them in a way that you could see happening and I think defend against. So I would think these would be far less vulnerable than anything that we do confined to the surface of the Earth. Think of the economic position of Russia, which is trying to put natural gas and oil through Ukraine. This has been a battle that's been going on even before the Soviet Union broke up. So in a situation like this that you can interrupt, here you could be in your national territory and deliver it to another national territory without interference in political boundaries.
How many reflectors would you envision would be up there when it's fully, if it was fully implemented?
Well, we're about a 4 terawatt electric world right now. And so I would think it would be on the order of a few hundred. Depends on the exact technology you use. There's a technology that lets you accept a microwave and then divide it into many others. And the more aggressive you can do the division, the fewer the number of satellites there would be. Mm-hmm. Yes, sir.
I'm almost embarrassed to ask this question.
Please don't worry.
Our wonderful hosts and my law school classmate, Judy, knows I'm in the carbon management business.
Uh-huh.
We moved 40 million tons of this product last year, both on trains and the ocean. A month ago, we filed an antitrust lawsuit against BNSF and UP, front page Wall Street Journal, over the cost of moving this product. It's heavy, it's expensive, it's environmentally difficult. So that part of your argument is incredibly attractive. And to answer Charlie's question, the largest contributor to Congress last year was railroads. And because they want to maintain this exemption on the antitrust, and they control whether it's chemicals or coal or cars, they control it. Having said that, the most practical question Mike asked, and that is, you know, obviously one of the things you have to do is to raise some money. And you're talking with a B. I don't know how many people in this room starting with B have a B to write to anybody. But having said that, the practical question that someone who can write a $1 billion check or can be part of an investment is going to be, is it my great-great-great-grandchildren who will get the return on this? Because it's one thing to get a demonstrator, it's another thing to do this, another thing to that. Next thing, and I don't understand paragraph 5, but whether it's and, which I think it is, that's a lot of B's. So if you get all that money raised, and it's only to demonstrate it can be done, how does the investor possibly get a return in our lifetime? Because most of us would say, we hope our lifetime's 30 more years, or 20 more years, or our children's or whatever, but how does an investor possibly get a return without regard for the technology, without regard for what it does for the world, without regard for how imaginative it is? How does an investor get a return?
Well, I think the analogy is to integrated circuits, in that you put a lot of money into the plant that builds the first one, but then it scales. And this is a very scalable technology. You don't have to, once you get the demo beam, the whole system grows by simply making these apertures larger.
But what's the first time, and I have a reason for that, what's the first time you think, if everybody said, yes, this is good, and they could write these checks, when's the first time you could commercially produce any electricity?
Redistribute, yeah. On the order of 6 to 10 years.
6 to 10 years.
Mm-hmm.
So has anybody thought about going to the electrical? Because I can tell you that the generators of electricity do not care about the railroads, do not care about the coal miners, do not care about the oil, do not care about the gas production. They only care about themselves. Has anybody gone and tried to sell contracts to them for money, looking forward and say, if I can produce this electricity for 1/10 of what it costs you, would you sign this contract and get any money from them?
The tool that John and I have talked about several times is the power purchase agreement, and there is one group trying to promote solar power satellites, and they have a power purchase agreement with which company? I've forgotten now.
It's a power company in Northern California.
Yeah, in Northern California. Those could be, I think, in principle obtained from government agencies, DOD, or companies probably in a cooperative manner. And that would be a guarantee that they would buy the power if you could deliver it to them. And that may well be the way that you have to approach it. But part of the reason of this meeting is to explore topics just like that, to talk to people like yourself.
We recognize that only 1 or 2 of you can actually write a check for B.
I look at you, John.
No, he's modest. He meant tens of these.
So the objective here is to introduce green energy transfer and to get introductions and to talk to the government, because if the government could give us a power purchase agreement, that would be as good as gold, and then you could take that to major corporations like Boeing or like Hughes and make partnerships with them and have them be investors in the company, and then ultimately get down to some cash need of a much more reasonable number and see what happens. But that's a little ways off, and Judy's giving me the high sign, and it's time to have coffee and cake.
I've been sitting for 45 minutes.
Yes, I'm sorry, it took longer than we thought to do this, but
No, it's very interesting.
I want to thank everybody for coming, and also, if you want to see what a patent looks like from Russia, we have a copy up here. And you can see it. We have some other things here. Also, there's a couple of flyers, one on the problem of the military getting electricity to remote sites in Afghanistan and the blowing up of their gas tanks. Another flyer is there was a proposal within the last week of moving some oil from Canada in a sand oil thing down to the middle of the continent, and the estimated budget on that pipeline is like $14 billion in quite a few years, and that goes from one place to one place, as opposed to a system which would permit you to go from any place to any other place. And so there's a lot of I have become absolutely unreliable as a source. I am so fond of David in this project that you simply just can't trust me. So in any event, David, we're going to hang around. Yes.
Just one last question. 5 years ago, David had talked about the increased energy needs of all the different countries, and China and the United States. And I remember there was a graph that it just went off the chart. I'm sure since then it's changed dramatically.
Yeah, it goes off the chart faster.
That's what I'm worried about. Yeah.
Yes, but that's.
Do you still have that?
One of the that's a much bigger B. Yeah. And our thought was that if we can get this system installed, then going to that step is a much easier step. And also it's commercial. Our system puts up satellites. Our system puts up television satellites and radio satellites, and it puts up communication satellites, and it puts up spy satellites. Putting up satellites is not a big deal. Viasat, a local company, is putting up a $450 million satellite next week out of Russia. And that's because we don't make rocket ships. I mean, we're so pathetic around here. So if there was a customer that was going to put up 20 satellites, you know, then maybe some of our own industry would be more interested in helping out. But yes, that system is still alive. It's going to work. It's the only, my prejudice again, you don't trust me. It's the only solution to an energy drained system. And that solution is available, and it's going to work, and it's just going to, that may not be in Roy's lifetime, but it will be in his kid's lifetime. Anyway, thank you very much for coming. Okay, there's coffee and cupcakes.